So good evening, and as I'm starting, I'm just curious how many people consider themselves kind of technically oriented scientist, engineer types? Show of hands. Look like a pretty educated crowd. How many people affiliate with the university in some way? Okay, great. Well, welcome tonight. Parts of this talk are structured for the general public, so a couple of disclaimers up front. One is I am not a PhD astronomer. I see one here in the front row, but no, I'm not. I'm an engineer by trade, and I'm a program manager. So you can easily ask me questions about astronomy that I will attempt to answer, but take what I say with a grain of salt. So with that, I want to say that we really do live in a remarkable time. Humanity has made just amazing gains in science and math and literature, philosophy, and it's brought us to a place where we're capable of doing things that people have thought about for a long, long time. So, today the landing on the comet is just a great example of the kinds of things that our civilization is capable of. Tonight I'm going to talk about Kepler, which I believe is a remarkable example of that. We really are, with Kepler, helping to set our place in the cosmos. And that's not light stuff. I mean, that's pretty cool, actually. So as far as the context, I believe that all the way back, maybe even the dawn of history, of recorded time, people have wondered when they looked up at the sky, are there other places like the Earth out there? They may not have fathomed that the Earth is a planet, et cetera, but I can't help but think they would look around themselves and wonder, are there other places? And here's a case where Epicurus back in 2,000 years ago said that we must believe that in all worlds there are living creatures and plants and other things that we see in this world. So even in the early Greek philosophy period, people were really wondering, are we alone? Is there other life out there? Kind of fast forwarding, still 400 years ago, to Kepler's era. Here was a gentleman who had a poor taste in dress by today's standards, but was just intrigued with what he saw around him, and he used his curiosity to help formulate just some of the most powerful math that humanity has ever come up with. And I love this quote: precisely in order that the human mind shall never be lacking in fresh nourishment, right? The curiosity that's embedded in that statement is just profound. So now, 45 years ago, now I'm 53, when I was a child, we knew of 9 planets around the sun. That was before Pluto got kicked out of the club. And a lot of people thought our solar system was unique, right? That this was a very, singular thing in the whole universe. Science fiction writers envisioned advanced civilizations on planets around other stars, both near and far, but there was no scientific evidence for planets outside of our solar system. So tonight I'm going to tell you how we've moved from 2,000 years ago, 400 years ago, and even 45 years ago to a very different understanding of our place. So Kepler is kind of based around this concept of habitability. And since we are water-based carbon creatures that live on this planet, we are going to define habitability as a place where water can exist in a liquid state. Now, I tell the high school kids that I talk to, I can imagine molten lava people living on some exotic planet, but since we know about ourselves, we're going to kind of look at this from an Earth-centric point of view. The remarkable thing about our solar system is the number of planets, but also look at the contrast between the terrestrial planets and the big gas planets. That's really telling us something, but it's also showing us that there's a great diversity in our solar system. So a lot of times I'll talk about that kind of stuff for maybe 20 minutes, but I figure everybody here has a pretty good understanding of why Kepler was put up there and what habitability is all about. But I think one of the things Kepler's helping us do is understand our Earth, and in order to understand our Earth, we really need other examples. You know, if we look in our solar system, we're not seeing other good examples, analogs of the Earth. But how do you find an exoplanet? Can you take a picture of it? You know, imagine a flashlight next to a lighthouse, right, where the lighthouse represents a star and that flashlight represents the Earth. You know, there's literally no way with our technology today. I think in the next 20 years we'll be able to direct image planets with either star shades or coronagraphs. But for now, we can't take a picture, which is pretty obvious. If you look at a picture taken by a space telescope, there's almost no way you could see an exo-Earth in the glare of that star. So how do we detect planets? Well, Doppler is the way that I think we found the first planets. Doppler is simply based on the principle that the planet and the star that it, quote, orbits really orbit the center of mass of the system. So, you know, we all think about the planets going around the stars, but in effect, they're both doing a dance around some common mass in that system. And as the star goes around that point, it's Doppler shifting its spectra. So part of the orbit, when it's going away from us, it's stretching the spectra. As it's coming towards us, it's compressing it. The problem with Doppler is you need a spectrograph, and spectrographs are notoriously inefficient. You need a very bright source to do spectroscopy. So a very powerful way to find planets, but also very limited. Now this one blows my mind, and anybody that knows about this can ask me a question that will exceed my knowledge instantly. But gravitational microlensing is becoming more common and more on the forefront of exoplanets. And I'll talk about K2 in a little bit, and we'll see how that ties into some of the K2 studies. But if a star and a planet pass in front of a distant source, and this is really passing in front of, it's a transient event, it creates a gravitational lens. That lens magnifies the source in the background, and by looking at how that magnification changes versus time, you can actually detect a planet. And it's cool because you can get the mass of that planet, which is very hard to do with transits, which I'll talk about next. So, up-and-coming way of finding planets. We've got Doppler, we've got gravitational lensing, and we've got Kepler's technique, transits. Interesting thing about a transit is it really is a fairly brief moment. You know, the Earth going in front of the sun is about 6.5 hours. So if you're outside of our solar system, in the plane of our solar system, staring at the sun, and the Earth were to pass between you and the star, our star, you'd see a dimming for about 6.5 hours. So that really is, you have to look at the right time, or you have to look continuously. The other thing is, if you assume that the plane of these exosolar systems could be oriented randomly at any orientation, there's a 0.5% chance that that plane is oriented along your line of sight from the Earth. All right? So if you were outside of our solar system, up above, looking down, you'd never see the Earth pass between you and the sun because you're at the wrong angle, but 0.5% of the time you would see it if they were randomly distributed. So the idea of a transit is to measure the light from the star and look for a dimming. Now to do that, we're going to do photometry. We're not going to do imaging. So this Kepler mission's not about a big imaging camera. It's about a very sensitive photometer. Jupiter passing in front of the sun is about a 1% dimming of the sun. The Earth, or Venus, is a 0.01%. So 20 years ago, you couldn't have done the Kepler mission because we could not have built a sensitive enough system to detect that small of a change in the brightness. And the other thing I think is fascinating is look at this sunspot compared to the size of Mercury. Right? It's really easy to fool yourself when you go looking for planets via the transit method. So in order to do that, you need to be very careful that you look for 3 transits. First transit could have been a sunspot. Another transit, 365 days later, could have been another sunspot, or it could have been a planet. But a third, if it really was spaced precisely in time, says that you've probably found a planet. Very unlikely. Now, there are other spoilers out there. For example, imagine a binary star pair behind the star that's got this planet. Well, that binary is also causing a fluctuation in its light curve, which could spoil your planet detection. So even though transits work, the physics is all there, there are things that can fool you. So I hope I've made a case. There's a compelling question. Are we alone? Are there other planets out there? I've shown you that there's techniques, 3 of them. In our case, we're going to pick transits for looking for exoplanets. So I think we have the foundation for a big question. What fraction of the stars in our galaxy harbor potentially habitable Earth-sized planets? So that's Kepler's mission. It's not to go find one planet. You know, that's been done and it will be done again and again. Kepler's job is to figure out what fraction of the stars in our galaxy. So the goals are to monitor over 100,000 stars with exceptional precision, because we're looking for a very small signal, without blinking, because 6.5 hours is the equivalent transit of the Earth in front of the Sun. And you have to look long enough for 3 transits. So we're going to look from small repeated dimmings in the light of the stars that turns out to about a 20 part per million dimming. So again, I get back to how sensitive this camera has to be. Now, if we do this experiment, for the first time we'll be able to know whether planets like the Earth are common or rare, at least in our galaxy. And for the first time we'll get some statistical information about how planetary systems may form. Right? So this experiment potentially has some pretty significant results coming out of it. Now, Kepler was built in Boulder. And a lot of people, you folks all know, but a lot of people don't realize that we have a spacecraft factory right here in Boulder, right? Think about how many cities in America or on this planet have spacecraft factories, right? It's a pretty unique thing that we have here in town. And I think when you couple that in with the work done at LASP, you really get a very unique situation where you have people flying the satellite in the same town that it's being built. So, simple spacecraft, telescope, spacecraft, solar panel. The photometer is a big Schmidt lens on the front, a big primary mirror in the back, and a 95 megapixel camera that points back. So as light comes through the lens, hits the primary, shines up onto the camera. Now what I love about this picture is how foolish this picture is, because anyone with some CAD software and PowerPoint can make a pretty picture like that. However, there's real hardware behind that, and it was a lot harder than just drawing a picture. So, for example, the Schmidt corrector, here it is being tested at Tinsley in California. You can't make big optics using mechanical metrology. You have to use basically interferometry to measure the precision you need for these big optics. So very complicated interferometric setups to both create it and, as Hubble taught us, test it. You don't want to have the perfectly wrong optic. Here's a picture of the glass in our clean room, right? Amazingly beautiful $1 million coffee table. But stop and think about it. You know this thing's going to go on a rocket, right? Rockets are violent, shaking events, launches are. And we're going to take this huge piece of glass. So how do you put a piece of glass on top of a rocket and safely get it in space? Well, in our case, we bonded titanium pads, 12 of them, around the circumference of the lens. And each of those titanium pads had a flexure on it, which is just a thin fin. And that then mounted to a composite ring. So that as that piece of glass vibrates during launch, or as the telescope vibrates on both sides of that interface, those titanium flexures just bounced up and down and kept the glass from breaking. Now, there was a lot of analysis that went into making sure that would work correctly. And there was a lot of testing. I mean, I have to tell you, I hate glue. Glue and coatings, optical coatings, are just, I hate them because there's always a contaminant or something wrong. It's just very hard to do. So we did, I think, probably 30 or 40 different test bonding of the titanium to like pieces of glass, and we pushed on them and tested the strength. And you know, it's a phenomenal process to kind of go from this to this and then safely get it to orbit. Likewise, the primary mirror. You know, here you are in a shirt sleeve environment in Pittsburgh with a big machine putting the surface on it. Here you can see it now that it's reached ball in the clean room. This big piece of glass had to be lightweighted. So Brashear, Corning, used water jets to make this thing about 14% of its original weight. So 86% lightweighted by using water, almost like a water pick, right, with a lot of force to carve out all these honeycomb patterns in this optic. Then you coat it. Again, I've shared with you how I feel about coating. That was a very intense period of time, and it was nice to have it coated, but nerve-wracking. And then here it is again in our clean room, getting ready to be mated up with the rest of the photometer. Our camera, right, starts out with little CCDs from England, built up in pairs. This is a piece of sapphire that's a lens that compensates exactly for that Schmidt corrector lens, so the two lenses work together. So we've got little lenses on the front of our CCDs. You put 21 of those together to make the camera. Boy, how hard can that be? You see how it's a curved surface? It took a year to machine the piece of stainless behind this that holds these in the optical form, because the act of machining put enough heat into the metal to distort it. So you had to distort it, measure it, machine it, cool it down, measure it, distort it, machine it, cool it down for a year before we had the shape so precise that we could build the camera. Now this box, or would fit in a box that's about 1.5 cubic feet, $38 million in this component, 22,000 parts. The front surface runs at about -100, the back surface runs at +20. Right, so we have a 120-degree temperature differential, we've got 22,000 parts, we've got precision tolerances, we've got cleanliness, right? Any eyelash, fingerprint could mess things up. And then we put it all together in this structure so we can hang it in the middle of the photometer. Now that is what the hardware really looks like, not the cartoon I showed you originally. Spacecraft, similar kind of thing, right? You've got your structures. Think about it, the whole load of the spacecraft gets carried by this ring down here, this collet, when you're put on the rocket and launched. So all your load path goes through here. So the structures involved had to be very carefully designed and tested. Here's the reaction control system, solar panel. Solar panel was tricky because most of the solar panels are flat plates, you know, flat plates, flat panels. But because we're using this as an umbrella around the telescope to kind of shade it from the sun, it has a very unique shape, really, really hard to make. For a while I was wondering if we were going to actually be able to make it. We were having so much trouble. It was manufactured in California, and it was really tough. The rest of the spacecraft, you got your computers, you got your clocks, you got your solid state recorder to store things, big antenna. The batteries are actually made of Sony laptop batteries. And they take a whole bunch of them and string them together and then pot them in a big thing of glue. So I used to have these nickel hydrogen batteries that were really dangerous, pressure vessels, very hard to deal with. These things are really remarkable batteries. And it is just a bunch of laptop batteries glued together. So spacecraft goes together. Again, how hard can that be? Think about how many thousand wires you're seeing in these pictures. And every one of those wires has a starting point, an ending point. There's redundancy where it fans out to multiple boxes. Very, very hard. Here are the reaction wheels, which I will come back to. 4 of them on the spacecraft. So now we're going to take our $160 million photometer and put it on top of our $100 million spacecraft very carefully with a crane and get ready. Take it to Florida, right? So when we finish building it in Boulder, what do? It's been behind a guarded room, you know, it's been behind guards, behind fences, in a clean room, constantly monitored. We're going to put on a truck and we're going to put on the interstate and drive it to Florida. Very happy when it got there. Then we take it out and put it on top of the rocket. Now this is a funny picture because this is a clean room that's 14 stories up in the air. You can see the folks down here working. This from here up is Kepler, there's the 3rd stage, there's the top of the 2nd stage. Very strange work environment to be out there. And there we go, launch 2009. Now, we left the Earth. It'd be a really lousy mission to do in the Earth. Hubble's got the Earth in its way half of the time. Every 45 minutes, Hubble's got the Earth between it and what it wants to look at. So Kepler's launched into a heliocentric orbit, Earth trailing, get away from the Earth, don't have the Earth in the way. You notice in these pictures that it's pointing up out of the plane of the orbit, and that's because the Kepler field was out of the plane of the orbit. So I'm going to take just a second and explain how the reaction wheels, the thrusters, and the solar pressure work, because that's going to be important when I start talking about K2. So imagine the telescope's looking up here. The photons from the sun are hitting it. That pressure is enough to try and tip us over. So the reaction wheels are spinning in the opposite direction and holding us in place. Sun tries to tip us over, reaction wheels hold us. Well, you can imagine the reaction wheels would have to spin faster and faster and faster until they were spinning infinitely fast. So every 3 days we use the thrusters to compensate for the reaction wheels and spin them back down. So the reaction wheels are spinning up, spinning down as the solar pressure hits the telescope. So that's how we maintained our pointing during the prime mission of Kepler. Every quarter we rotated 90 degrees, so we'd always have the sun on the solar panels. Also look here, well actually I have some good pictures here later. But anyway, it's important to think about Kepler during the prime mission as the solar pressure trying to tip it over and the reaction wheels holding it up. So where are we going to look? We're going to look in the Orion Spur. It turns out that's where the nice density of sun-like stars were. If you looked in towards the center of the galaxy, it would have been too many stars and they wouldn't have been the right type. Since we're looking for Earth-like planets around sun-like stars, this is where the astronomers said the best place to look was. Kepler's looking in a 3,000 light-year cone, so we're not going to find stuff that's in our neighborhood necessarily. These stars are a long ways from the Earth. So here's a light curve, right? Look at that number there, right? If 1 is the normalized amount of flux, we're talking about a tiny little decrease. You can see some spikes. These are safe mode events or other interruptions. But if you look carefully, those dips happen every 45.29 days, repeatedly, till the cows come home. Over and over and over again. That's a planet. Now, if you use Doppler, and in this case we could, and couple it with the transit data, you can figure out the density of this planet. This line here is an Earth-like rocky planet, terrestrial planet composition. Here's Mars, here's Earth and Venus, here's Kepler 10b. We found a rocky planet. Now, if we looked at the Earth tonight, we might have had an ice planet out here someplace, right? So pretty cool, right? I mean, we actually can find a planet on the other side of the galaxy, and we can tell you that it's made out of the same kind of rocks material that planets in our solar system. So in 1989, there was one exoplanet. Between 1989 and 2013, excluding Kepler, there were a lot of planets found. Most of them large, long orbital period. When you add in the Kepler data, you get this. So I think we accomplished what we set out to do. So obviously lots and lots of planets, and these are planet candidates, so not every one of these have been vetted and proven to be a planet. The scientists are very particular about not naming a planet before it's time. However, if you ignore some of the obvious artifacts, like this planet here that's got no radius, or this planet here that's got a 0 period, and I don't know why those are on this plot. I keep thinking I'll go back and ask. But if you look up here, and there's planets out there that are bigger than Jupiter that orbit their stars in a day. Think about how big that is and how fast it must be going to go around its star in a day. And it's not just a few. I mean, there's quite a few. So there's an amazing diversity of planets out there. Another way of looking at that, and maybe we go all the way back here 2,000 years to the Greeks, right? Or maybe even Kepler's time or Galileo developing the telescope. Coming along, and then boom, right? I mean, we have changed astronomy, not just Kepler, but all the people that have developed the exoplanet science. In the last 10 years, an entire new branch of astronomy has just come to be, right? Very cool. So as of tonight, there are 1,849 planets, or at least I think that's how many there were. Somebody may have announced one today. They're in 1,160 systems, so we've got multi-planet systems. And as I said, there's all these candidates sitting out there. The false alarm rate is maybe between 10 and 20% right now. You know, there's a lot of argument about that. So not all of these are going to end up being planets, but if you just kind of blink and assume that, let's say 70%, that'd be a conservative, that's still going to be a lot more planets added in there. Every one of those is now something a grad student can go look at and study, right? I mean, we've really expanded what astronomers can look at. And importantly, we're not just telling them that there's a planet, but we're telling them when it goes in front of the star, right? So we can predict when the transits are going to occur. So if you wanted to do spectroscopy, where you're doing differential spectroscopy between the star plus the planet and just the planet, you now know when to do that observation. You don't have to sit for 365 days and wait for the transit. So, Kepler 62 system, you'll notice here the star is a lot smaller. The green represents the habitable zone. Here we've got 5 planets in this system, and 2 of them are in the habitable zone. It's a long way from Earth. We're not going to go visit anytime soon. It's 40% bigger than the Earth, and a year on that planet, you're going to have a birthday every 272 days. Another example, this one got a lot of press, 186F. Again, smaller star. Planet now in the habitable zone, kind of at the outside of the habitable zone. The star's a lot dimmer. They say that at high noon on this planet, it'd be as bright as an hour before sunset on the Earth. So, have a thick down coat. But it's only 10% larger than the Earth. So here's an Earth-sized planet in the habitable zone in a star that's 500, around a star that's 500 light years from the Earth. So, what's our legacy? Well, about 20% of the Kepler planet candidate stars have multiple planet systems, which turns out to be kind of cool because as soon as the scientists realized they couldn't do Doppler follow-up on a lot of these candidates and these stars because the telescope, you know, Keck, you can only get so much Keck time and it takes a lot of time to do the spectroscopy, they started looking for other ways and they came up with this thing called transit timing variation. Transit variation timing, TVT. And what they're doing is they're looking at the transits from multiple planets and doing computer simulations to figure out how big they are and where they'd be spaced in order to give us that signature. And using the supercomputer, they're now able to confirm planets in multi-planet systems by just using the transits. Don't need the Doppler anymore. Pretty cool. So Kepler's also found that 50% of the M dwarf stars, which are, you know, roughly half our size of our sun, have an Earth-sized planet defined here as less than 2 Earth radii. Since there are 70 billion M dwarf stars, that says there are at least 35 billion Earth-sized planets out there. Right? So there's the statistics that Kepler's after, right? No longer are you saying, gosh, I wonder if I look up at that star if there's a planet around it. You know that, well, that one has one and that one doesn't and that one does and that one doesn't. I mean, the sky is full of stars with planets around them. Now, I just finished reviewing the Q1 through Q16 catalog. It's going to come out in January. This is the first one that uses all the Kepler data. It's not going to have a whole nother order of magnitude, but boy, is there some cool stuff. I mean, it really does put a bow around the overall Kepler mission in terms of the catalog. So that's coming, I think, January LAS, it'll be out. I couldn't help but put this picture up. I mean, just amazing. I don't know how many of you saw this in the news. This was released last week. Alma took this picture. You know, it's not visible light, obviously. But look at how the planets are forming around this star and collecting up the dust and making these, I mean, just amazing. So Kepler is showing us there's lots of planets out there, and here we have a completely different observatory taking pictures of protoplanetary systems as they're forming. Really cool stuff. All right, so now we're going to shift into Kepler K2. So now for something entirely different. So when a good wheel goes bad. This plot shows the 4 reaction wheels on Kepler. This is the speed that they're moving, and this is basically time, day of year. And right here, everybody's behaving. And then reaction wheel 2, which is the green line, starts to misbehave. And as it's misbehaving, and by misbehaving I mean increases in friction, the other reaction wheels, the whole telescope starts to shake, and the other reaction wheels are compensating. And for about a day, it struggled, and then here, that reaction wheel went to a 0 speed. So we launched with 4, we need 3. So let's keep going. This was July of 2012. Actually, our pointing performance improved because we had one fewer reaction wheel causing noise in the optical pointing. So then, on May 11th in 2013, we're going along. We'd had some inkling that that our reaction wheel 4 might have some issues, but nothing huge. But boom, just instantaneous stop. Now we're at 2 wheels. And again, note May 11th, 2013, May 15th, 2013. Kepler spacecraft on the verge of death with OJ. May 15th. Call a medic. May 18th. 9 emails. This is from my email archive, including things like potential answer to Kepler. We did this on GFO, which was another satellite that Ball built. Okay, here you go. And here's why it works. So I have our staff consultant at Ball, who's our expert in ADCS systems, 3 days after verge of death, sending me emails on a Saturday, 9 of them, within about a 6-hour period, and he lays out right here, just boom. Here's how you save the mission. Pretty cool. I wish it was that easy, but he sure got us started down the right track. So the question is, how do you point when you only have 2 reaction wheels? Well, we're lucky in that the 2 wheels that remain control the bore sight. So we can go left, right, up, down, till the cows come home with the reaction wheels. What we can't control with the loss of the 2 wheels is the roll of the telescope around the bore sight. However, if you use the thrusters, and we launched with extra fuel, to inject momentum into the system, so we're going to spin those 2 wheels up so that we're stiff, right? I mean, you've got a lot of momentum. It's going to help minimize how the disturbances in the system cause you to drift. You can go 4 days without thrust. I'll put a caveat around there because you're going to see that I'm actually using the thrusters more frequently. The wheels are going to start at a higher speed, and they're going to ramp down as the solar pressure hits the spacecraft and takes that momentum out. So it's really not that different than what we were doing before with the solar pressure causing the wheels to spin up and using the thrusters to spin down. We're doing the inverse. We're spinning the wheels up to get a lot of stiff momentum in the system, and then the solar pressure takes it out. And after a few days, we've got to spin those wheels back up again. Low fuel consumption. And we're going to use the solar balance in X and Y to minimize that rotation about the bore sight. Highly stable in all 3 axes. We're going to optimize it to minimize the jitter. And maybe we can even use the fine guidance sensors, which I haven't talked about. I'll try and find a way to tie that in. So again, we've got a cartoon. Another cartoon. Right? Think about that motorcycle with the fairing on the front of it, right? As that photon pressure comes around it, if we are perfectly oriented, we can use those solar panels like a fairing to kind of move the slipstream around us and stay balanced. I love these cartoons because that's what it really looks like. Right? There is nothing aerodynamic around about the bottom of this spacecraft. right? Up here in the solar panels, yeah, I'll give it to you. It's a thing of beauty, but you know, all these boxes, everything that sticks out.
Is it at least symmetrical?
No. Definitely not. Close, but it's balanced.
Yeah.
All right, so now I probably have a way to point, right? Got some work to do, but I got a way to point. So now let's see if we can create a mission around this. So the idea would be we can no longer point out of the plane of the orbit. We're going to point in the plane of the orbit. And as we go around the sun, the sun angle between the back of the telescope, where you no longer have light on your solar panels and you don't have any electricity, or as the sun moves around on the front where you get sun down the barrel, that's going to limit us to about 82 days per field. So every 82 days, I got to move from this field to this field to this field to keep the sun from going someplace it shouldn't. So I'm going to call these 82-day things campaigns. You'll see them referred to as campaigns or C1, C2, etc. Now the other thing is I'm going to be looking in the velocity vector direction or the anti-velocity vector direction. And it turns out that most of our campaigns are like this, where we're looking in the anti-velocity vector, but there's going to be one campaign where we flip around and look in the velocity vector. So that was, you know, we talked about May, and then there was June and July. So by September of 2013, kind of has some ideas in our head. But now it gets even harder, because it's no longer just engineering. We have to create or implement a brand new mission by December of 2013, just a few months away, in order to be invited to NASA Senior Review. If we're invited, we have to submit a proposal just 1 month later for how we're going to do the mission. And by the way, NASA's broke. Right? So every mission going to senior review had better do a good job, because there isn't a lot of money to go around. And they're not in the mood to just kind of hand out the money. It's clear NASA will not continue Kepler as an engineering experiment. So there has to be a strong science case. So in parallel with working the engineering side of things, we solicit the astronomical community for ideas where you could do some science in this 82-day campaign that we were talking about. So we got 39 10-page papers. Dennis and I were on the review team for the papers. Great stuff. Some of it was a bit out there. Some of it was not possible because they wanted to go look at the old Kepler field, and in this mode we couldn't do that. But carved out a science program, started to see the seeds of a science program. So now we need to kind of go into a test program. We've got to figure out how to get from here to there quickly. So our test program had to be efficient, had to be success-oriented, was going to take a higher risk, and it had to demonstrate the science. In order to do this, Ball engineers and the folks at LASP, I see Sean back there, had to work just like this, because we didn't have time to do the 3 months of practice and preparation and review. I mean, it was, what are we going to do 2 weeks from now? Oh, we just saw this data, now we got to go. So it was much more joysticking than any typical NASA mission, much more than Kepler started with. So the goals of this test program, first we had to establish a new concept of operations. I mean, the antennas on Kepler were oriented so that we'd always have great coverage when we were looking like this. Now I'm going to be like this. It turns out I have horrible antenna coverage for the low gain antennas. So now I've got to go from pretty much always being able to do something with the vehicle to, well, now during this time period that I'm doing science, I don't have contact with the vehicle. So I'm going to go to a more of a stored command sequence point of view instead of just doing the same thing over and over again like the Kepler thing. I got to prove this thing's going to work, right? I can't show up in December and say, yeah, I still got some great ideas, trust me. I got to refine and calibrate the pointing control. And I need to get some science folded in here, because I got to convince the scientists on the senior review board, they aren't engineers, they're scientists, that this thing is going to work. So everything's looking promising, but there's lots of questions. How do we balance that photon pressure with this asymmetry on the back of the vehicle? How do we get the thrusters to control roll only, right? You're going to be firing these thrusters, but there's coupling in the system. So you're going to get some bore sight motion when you fire the thrusters, even though all you're trying to do is do roll. How do you minimize the fuel use and maximize the pointing? You know, there's ways of doing this that uses a lot of fuel, and boy, you get great pointing, but your mission's over instantly. How do we do communication at the science attitude? These fine guidance sensors. So during the Kepler mission, Kepler has star trackers and it's got fine guidance sensors. The fine guidance sensors look through the point of sight, the line of sight of the telescope, and basically centroid multiple stars, and as you drift off your desired pointing, the air signal gets fed back into the attitude control system to lock you on. It's the same system that Hubble uses. Kepler is as good as Hubble during the prime mission using that system. So you're using starlight on CCDs to help control the pointing. Now, our first blush, we're going to be drifting too much to use that system. So it was always a goal to see if we could find out how to use that system here, but it was definitely a stretch goal. It was not obvious we were going to get there. So we actually designed our science case around not getting to fine guidance and actually having a fair amount of drift or deadband going back and forth in the pointing. Another thing that was tricky was Kepler had a pretty uniform solar angle or orientation, thermal orientation with respect to the sun during the prime mission. Now, I told you the sun's going to be going from the back of the telescope or back of the system all the way across the system towards the front. That causes thermal distortions through the whole system. So the star tracker to bore sight alignment of the photometer is now changing as a function of day of year or sun angle in some pretty big ways that we had never planned on. So if we safe in the middle of one of these campaigns and have to disrupt, it's not obvious we're going to be able to get everything lined back up and get going again. Very tricky. So one of the things we did is a solar balance calibration test. So we did the teeter-totter test. We actually moved the sun across various points and we calculated where the optimum roll was for that area. And instead of keeping the sun on that line right along the apex of the solar panels, it turns out we're about 2 degrees off or 1.5 degrees off. We tip up a little bit, and that tip is just enough to be on our teeter-totter balance point. So we had to calculate what that point was, and that's what this line represents. So what I described earlier with use the thrusters to spin up the wheels, I call that a resaturation of the wheels, and that originally was going to be the only time we used the thrusters. Well, if you look at this plot, this is basically roll error, and the green is our requirements, our new requirements. So as long as we're in between these two, the scientists are more or less happy. Here's the resat, where I stop and respin up the wheels every 3 days-ish. And during these periods, we have uncontrolled roll, basically. And that's manageable, except we found that if we did a tweak, which is just basically a thruster correction, a small thruster correction, periodically between these resets, we could actually improve the pointing. So what you're seeing here is the resets and the tweaks and the periods where we're drifting in between, and staying quite nicely between our bumpers in our bowling lanes. Now, if this works well enough, we're going to keep those guide stars on the fine guidance sensors, right? If we drift too much, the star on the guidance sensor will drift off the guidance sensor and I won't be able to do fine point. But if I can manage this tight enough, I'll keep those guide stars on the fine guidance sensors and be able to do fine point. So K2 is born, right? You know, up until now we hadn't really named it yet because we had a concept and we had some science and we had a mission, but we hadn't really put it all together. So in the fall of 2013, the science program was baselined. It includes, it's kind of, you know, I'll pat ourselves on the back a little bit. We went out and we really embraced the community, right? We're no longer an exoplanet mission. We are a general purpose astrophysics observatory. My advocacy group just increased incredibly for that senior science review, right? What's more, we can't afford to build a big data processing pipeline that's going to calibrate all this data for all the astronomers. We're going to let them roll their own. We're going to say, we're going to give you the data. You propose, we're going to give you the data. You've got to do your own data processing, but we're going to give you money to do that. So we tie in soft money and a general astrophysics mission, and suddenly we had people coming out of the woodwork that wanted to use K2. So the 4 categories pretty much are transiting exoplanets around M dwarfs. I'll come back to that in a second. Open clusters and star formation. This is something Kepler was never really designed to do, but wow, you could do some pretty good science with a large format field of view telescope that's got stable pointing, a photometer. So here's what we look at as we go through our 82 days, and each of these little postage stamps is one of the campaigns I was talking about, field of views for the campaigns. And if you notice, some of them fall into the galactic plane, and some of them are way the heck out in the middle of nowhere. So these are the extragalactic opportunities, and these are the star formation, and the M dwarfs are just everywhere, right? So suddenly we really do kind of almost every other campaign, we're switching between looking in our galaxy and looking out of the galaxy. So you could do T0 supernova time studies, right? Look at other galaxies, look for supernovas going off. Since we have such a big field of view and we can look at so many targets, odds are you might catch a supernova going off, right? And now you've got its light curve right when it went off. The microlensing, well, it turns out for field 9, I don't know why it's not labeled field 9. It kind of comes back here. We're looking at a very, very dense part of the galaxy, and it turns out to be a really good place to do microlensing because there's so many stars. So WFIRST is going to do a lot of microlensing. Kepler is going to pave the way for some of that. In order to do that field, we're going to flip around from being in the anti-velocity direction into the velocity direction because it's on the other side of where we would have been looking if we'd been in anti-velocity. So we mapped out these fields, you know, a little bit of something for everybody. So the red dwarfs, you know, we started out with Kepler looking at sun-like stars. Well, red dwarfs are interesting because they're so much smaller, their habitable zone is closer, and those transits are happening in a period of weeks instead of months or years. Well, I'm doing an 82-day campaign. I need something that's transiting more frequently, right? So the M dwarfs are perfect. And you get a deeper transit because the area of the star to the planet is more favorable. So, you know, I think we're lucking out here a little bit. And M dwarfs are really abundant, right? You know, and they're close. You know, TESS is going to be looking at a lot of these things. So Kepler can start doing some of the pre-TESS, pre-JWST. If you really want to do spectroscopy on a planet or a system, closer the better, and these are great candidates. So in June of 2014, K2 was approved by the Senior Review. When you get a lot of money, we're running this thing on shoestrings, right? Which you really couldn't do if you had a big organization. You know, between LASP and Ball, we're agile enough and small enough that we could make it fit in the box. So basically, we're funded through government fiscal year 16. If I got that right, I'll have to think about that, but I don't want to think in real time. 2 years from now, basically. Gives us about 9 campaigns, yet they said, come back to us for another extension, which, if things go well, and we still have 2 good reaction wheels, and we still have fuel. The fuel is actually looking really good right now. So we're actually using fuel at a slower rate than what we had assumed we were. So I think it's going to go well. You know, one thing, we're getting further and further away from the Earth, as Sean knows. So the communications get harder and harder, right? But we planned on that, and there's ways around that. If fuel's gone, you're done. So for C2, campaign 2, here's just a breakdown of the proposals and the targets that we got. Long cadence, LC, are our 30-minute data takes. You know, if you're looking for 6.5-hour transits of Earth-like planets around sun-like stars, 30 minutes is a great cadence. Yet Kepler's always had a short cadence, which is a minute data collection. And that primarily was to feed the astroseismology guys, right? And also to do some of the transit follow-up stuff. But so we have really two modes of data collection. They happen simultaneously, so I shouldn't say modes, but two options for data collection, a fast and a slow. The problem is that these use up a lot of storage, so we typically don't have as many of these as we have of these. So astroseismology, solar system, exoplanets, clusters, stellar activity, binary stars, extragalactic, right? Little something for everybody. These are the proposals we got for C2. So we put out the call, people submitted proposals. This isn't kind of a notional thing. This is what people really want to look at. And for each of these proposals, they submitted their targets. And that's just the difference between here and here is what they proposed and target. So you can see the exoplanets at 24% blow into 76% of the targets. That's okay. And then for the short cadence, you're going to see astroseismology tends to be the dominant use of the targets.
How many targets are you doing in a campaign now?
So I think our goal was 10,000. And I'm not sure right where we're at on that. It's not too far away.
But it's much smaller than the...
Yeah, for a couple of reasons. One, our pointing's not quite as good, so we need a bigger aperture around the stars because you're gonna drift around in that aperture. The second thing is, and I haven't said this, we used to do these quarterly downlinks, right? But now I'm gonna go 82 days. We did monthly downlinks and rolled every quarter, but every month we stopped and sent the data to the Earth. Now I'm going up to 82 days without sending the data down, so I have to use my recorder to last that whole time.
Did you have to turn away a lot of requests for the use of it?
So I think the oversubscription is maybe 20 to 1.
Wow.
So, yeah, and they're just getting in. I think C0, C1, and C2 were kind of a pseudo tac, but starting now, it's been announced through Roses, and there's real tax, but I expect this oversubscription. It depends on the field. The extragalactic fields aren't quite as popular, but the stuff in the plane is. So who would have ever thought we'd be using Kepler to do solar system observations? Right? So if it passes through our field of view, you can set up an aperture that tracks it, right? We just looked at the comet sighting that went past Mars, right? Mars went through our field of view. Jupiter's gone through the field of view. Snow White is going to go through our field of view. I don't even know what Snow White is, but boy, it's going to be fun. So this is campaign 3. So campaign 2 finished today. So campaign 3 is starting up in the next day or so. We've been able to hand off from the trackers to the fine guidance sensors routinely. It's never easy, but that speaks to that thermal distortion between the trackers and the bore site. Our fine guidance works through those tweaks. I mean, that was one of our other fears, is that when we pulse the system, it would be enough to knock us out of the fine guidance. So the fine guidance appears to be holding. It really does. And with these 82-day campaigns, we don't get a lot of time to check on the system. I mean, you kind of send it off on its way, and you hope that the few times we get to see what it's doing what we want, because we can't really recover if it isn't. The pointing stability keeps getting better and better. I mean, I've seen data that's even better than a factor of 2 of Kepler. And again, Kepler was Hubble-class pointing. So with our little kind of kludged together baling wire system with the sun trying to balance us and this stuff, I mean, we are really rocking the pointing here. We figured out how to do the campaign checkouts in the ecliptic. Originally, when you start up one of these campaigns, Kepler, the first 4 quarters were really hard because we'd never pointed at the telescope at that part of the sky in that orientation. But as we got into quarter 6 and 7 and 8, we were starting to revisit places we'd been before, and it got easier and easier. With K2, every time we point this thing, we're pointing at a new part of the sky. The trackers are looking at a new area of the sky. The bore sight's looking at a new area. We could have different scattered light. It's like a brand new day every time we start a campaign. So originally, we were going to go to the field, take a little data, point back to the Earth, downlink the data, figure out what was going on, make sure it was good, and then go back to the field and do the science. That's pretty fuel expensive. So folks figured out a way to actually do the checkout while in the science orientation. we've taken, this is kind of where Dennis was just going, we've taken the number of targets, the aperture size, and the fuel usage, and we've kind of optimized all those things. And in fact, I just saw some numbers today. C2 used 96.6% of the recorder, right? So considering how many unknowns are there, that's pretty amazing that we, we're willing to overflow it. It wouldn't be the end of the world if we overflowed it, but that's pretty cool. So bottom line, we developed a brand new mission in 6 months and sold it to NASA, and here we are up and running. This is a C0 full field image. So just gives you a feel for...
CCD is dead then?
Yeah, this one's dead, and shortly after this picture was taken, this one died.
Okay. High dark current, or did it just fail? Just gone?
Yeah, we think it's in the power feed for that CCD. A lot of stars out there. A lot of opportunity. So with that, I'll take questions. Yeah?
What's the estimated time frame on fuel?
So I said that we got funded for 2 years, and I'm thinking we've got about 2 3/4 years if things go the way they do. The reason I'm hedging a little bit is safe modes are unplanned and very expensive from a fuel point of view. So, knock on wood, we've not had a bunch of safe modes. But if you have a safe mode and it's a long time between when you're talking to the vehicle, you can use a fair amount of fuel before you get back to it. Yeah, Chris.
Back in the early days of our development, we had an articulated main antenna, and that got dropped because of budgetary reasons. How much better would this mission be if we had that articulated antenna now?
So a couple things. One, let me go back in the history machine a little bit. As you said, it was dropped because of budgetary reasons. The other reason it was dropped is I'm completely convinced it was made out of unobtainium. The vendor that was building the antenna for us was having terrible problems. And they had told us, oh gosh, we know how to do this. And as we looked under the hood, it was getting uglier and uglier and uglier. So I'm not sure we could have really built that gimbal. And if we had, we would have been canceled because of those budgetary problems. Now, to answer your question, I'd love to have a gimbaled antenna because I could do science and downlink simultaneously. It would have been beautiful during the prime mission even, right? But it was just a bridge too far. And Kepler never would have happened with that antenna. I'm pretty convinced of that. Yeah?
So part of that is we lose 48 hours every 72, or every 82 different point.
Yep. Yeah, so it directly takes away from science time. Now, I think it introduces a simplicity to the mission. I'm also having problems having a gimbal built for another mission right now too. So, gimbals can fail and cause all kinds of headaches. They're more expensive to plan on their usage, et cetera, et cetera. But one way or the other, we got what we got. So, yeah, next question.
With Kepler pointing in one direction for 82 days, are you limited in the orbit of the exoplanets you can now discover by 3? Looking at 3 transits?
So with the original mission, it was 3 transits, no debate, right? Had to have 3, right? I'm starting to hear them say, well, 2, Now, and the reason is because if the stars are closer and you get 2 pretty good transits, maybe you take a ground-based observatory and you go look at the right time, right? So I think that we have more of a synergy with some of the Earth-based observing than we did with Kepler. I don't know. I think scientists will do what they can to get whatever they can, right? But you're right. You take the 82 and you divide, and we definitely are not going to find, stuff that's further out around bigger stars. There's just no way to do it. Yeah.
So one of the most interesting numbers to me is the fraction of the stars that you're monitoring that appear to have transits. And in one of your slides at the beginning, you showed that just on the geometrical probability, if it's random, it's like 0.5%, 1%, and I realize it varies a little bit, type of star and distance of planets. But one of your other slides showed, 1,800 planets around 1,200-ish systems confirmed, and another 3,200 candidates. That's about 4,000-ish
Out of
stars
150.
out of 100,000 or 150, that's 4%, maybe 3%. So it's looking like you could argue that every star must have planets if the statistics,
Right.
just based on random orientations, you're seeing more than you would have expected.
Right. So I got that exact same question at Chautauqua 2 nights ago, and you're absolutely right. You know, when it rains, it pours. I mean, it looks like
That's a stunning result.
that planets are really, really common.
Yeah. And unless there was something like a weird binary star or something to disrupt it, that the normal process.
Which is taken into account in a lot of these catalog papers, right? I mean, they take into account false, you know. So, yeah, when it rains, it pours, right? I mean, I remember wondering, well, maybe Kepler will find a few planets, right? The other slide I dropped out of here was a SETI slide, right? Because, you know, when I was in high school, SETI was going to go off and look at random places to see if they could find life, right? And I thought, well, Kepler's going to help because we'll tell them where to look. Well, we just told them to look everywhere. Questions over here? Yeah.
How intense was the flight software switch, since you didn't ever intend to do like the load command loads and all that kind of stuff?
So great question. The answer is we didn't have to change the flight software at all, right? And that enabled us to do what we're talking about. We crafted a mission that was completely modified or born with just table loads and parameter changes and operational concept changes. No software change. Phenomenal, right? Again, I'm talking about luck, right? You know, maybe it's luck, maybe it's destiny, but yeah, no software. Great question. Other questions? Yeah.
I may have missed a little bit of what he was saying, but I'm curious, with all of the planets they have discovered, how much information is available and where would we be able to go find that information?
So, I'm going to answer that a couple ways, right? If by information you're looking for basic astronomical information of where it is and when the transits are, there's a archive at STSCI, the Hubble Space Telescope Science Institute, called MAST. It's the Mikulski Archive for, I don't know what the ST stands for. Anyway, Barbara's archive at STSCI has all of the Kepler data in it. And in addition, the exoplanet folks at NextSci at Caltech, IPAC-ish, also have a very, very broad exoplanet catalog. So those are the places you can get the catalogs. And it seems like that was answered your question. The question that you might have asked that frustrates me a little bit is that we're still at the realm of Kepler 62F, right? I mean, they haven't been named. Right? We really don't know much about it. It's going to take, you know, maybe it's going to take 100 years before these things cease to be some obscure entry in a catalog and they really become something tangible, right? And slowly that's going to happen, but I feel sorry for all these anonymous planets out there. Other questions? Yes?
Are the orbits randomly oriented or are they biased toward the galactic?
Our assumption was they were randomly oriented. I don't know. I mean, there's probably somebody that's into planetary formation, but the galaxies are fairly.
Seem to be. I don't know of a reason to expect that there'd be a preferential orientation.
That's a great question, but
we're out of whack with our galaxy, so.
Yeah, I think it's a fair assumption, but I don't know if we know the answer. Right?
Yeah, because I was just thinking angular momentum in the plane.
Yeah. But there's a lot of other kind of disruptions that happen too, right? So, other questions? Yeah.
So with the original Kepler sensitivity, when we were looking at transits, we were also able to see sort of the anti-transit as a planet went behind the sun, sort of the mid-Saturn star. Can we do that in K2?
Yes, absolutely. So for those M-dwarf planets that we find, we'll see both the planet occulting the star as well as the planet disappearing behind the star. And the good news is that if those M-dwarfs are closer and we can really nail down the transits, then you can go use Keck or HST or Spitzer to do the spectroscopy during the transits and start look for atmospheric constituents, right? I mean, the science is really going to be enabled, I think, by the fact that these things are closer and you can actually do good spectra of them. Anybody else? Well, thanks for coming out tonight. You know, it was a cold, snowy night, but I appreciate everybody being here.
Thank you.
Yeah.